Let us discuss question 13 now. It says match the thermodynamic processes taking place in a system with the correct conditions. In the table, delta Q is the heat supplied, delta W is the work done and delta U is change in internal energy of the system. Well, all pretty standard symbols that have been used in this particular question. The processes have been listed here and the conditions are listed here. We have to find the correct match of the processes with respective conditions. Let us look at the first process, and of course clearly the question is from the topic thermodynamics. So, the first process is adiabatic, and what defines adiabatic process is delta Q is 0. That means for the first entry delta Q is 0, option B in fact, or rather entry B is the correct match, and other entries do not really match because delta W we can't say is 0. Similarly, we can't say delta U, delta W and delta Q, in fact all three are non-zero. That means C cannot be a correct match for adiabatic process, and delta U is 0 is also not a correct match for the adiabatic process. Let us look at the isothermal process. For isothermal process, change in internal energy is 0, the change in temperature is 0. So, that means for 2 D is the correct match, okay, and again other entries do not really match as far as isothermal process is concerned. Coming to the isochoric process now, we know that the volume is constant and the work done is 0. So, delta W is 0 for the isochoric process, which means for 3A is a correct match, and again other entries do not really match as far as the isochoric process is concerned. Finally, coming to the isobaric process. For the isobaric process, we can say that delta W is non-zero, delta U is non-zero and delta Q is also non-zero, which means for 4 C is the correct match. Now, let us look at the options. Among all the options, clearly option 2 is matching with our match. So, option 2 is the correct option for this question. It is time now to go to question number 14. Question 14 says a capacitor C is fully charged with voltage V naught. After disconnecting the voltage source, it is connected in parallel with another uncharged capacitor of capacitance C by 2. The energy loss in the process after the charge is distributed between the two capacitors is, and the 4 options are given. Clearly, the question is from electrostatics and it is about sharing of charge and achieving a common potential. The expression for the common potential when two capacitors are connected parallel to each other is given as the common potential V is C1 V1 plus C2 V2 divided by C1 plus C2. Now, in this particular case, this V2 is in fact given as 0. C1 is C and V1 is V naught. That means the common potential is then coming out as CV naught divided by C plus C by 2. The other capacitance has value C by 2. That means this is 3C divided by 2. So, 2 goes upstairs. That means the common potential is then 2 V naught divided by 3. The loss in the energy is initial energy stored minus final energy stored, and the expression then we can give as the loss in energy as initial energy minus the final energy. The initial energy is half CV naught square. The final energy is in fact half. The total capacitance becomes C plus C by 2 or 3C by 2. So, this is 3C by 2 into the common potential square, that means 4 V naught square divided by 9. After doing the subtraction and some amount of manipulation, well, this expression comes out as equal to 1 by 6 CV naught square. So, option 3 is correct for this question. I hope the solution is clear. Let us go to question number 15 now. And question 15 says, in a photoelectric effect experiment, the graph of stopping potential V versus reciprocal of wavelength obtained is shown in the figure. As the intensity of incident radiation is increased, the four options are there. Let us read out the options. The first one says slope of the straight line gets more steep. Second option says graph does not change. Third option says straight line shifts to left, and the fourth option says straight line shifts to right. Well, the graph does not change really. In fact, let us write the equation for the straight line, and from Einstein's equation we can say that V, the stopping potential into the charge of electron, VE, is equal to hc by lambda, which is the energy of the photon incident minus the work function. And that means the equation for the straight line is V equals hc by E into lambda minus phi by E. Clearly, this straight line equation is not at all dependent on the intensity of the incident radiation. So, that means the graph does not change at all. So, option 2 is the correct option for this particular question. It's time now to go to question number 16.